Okay, hello everybody. Thanks for tuning in. I just wanted to, before we start lecture two today, highlight a resource that I found that is really incredible and replicates pretty heavily like what we're doing in this seminar. So, Math at St. Andrews University, or no, just at Andrews University, has this playlist on algebraic topology, and this is literally everything that I want to go through over my winter break that I'm doing in this seminar. Um, the main reason why I'm going to keep like doing these videos is because I like working through books and I like kind of building up the ability to work through books. And so I'm kind of like planning to do the lectures every day the way we've planned out. But then go on and like that night watch this guy's videos to see like, oh, like is there something that like I did wrong, or maybe like I'll watch it ahead of time, just kind of as a supplementary thing. Um, but yeah, check it out. It's really incredible. Dr. Bosman um, really just does an incredible job. So, anyway, for those interested, today we will be finishing up chapter 0 of Hatcher's Algebraic Topology. Add this device. And yeah, it should be a lot of fun. So we ended on the topic of operations on spaces. And so we talked, and I'll share my screen, but we talked last about the suspension of a space. So just recalling where we left off. So we had products, are products of CW complexes or CW. Quotients are CW. And then suspensions and cones are both also CW. So yeah, maps can be suspended. That was like another construction that we had. And now we'll continue this with operations on spaces. Continued. Yeah. So the join. So the cone CX is the union of all line segments joining points of X to an external vertex. Similarly, the suspension is the union of all line segments joining points of X to two external vertices. More generally, given X in a second space Y, one can define the space of all line segments joining in X to points in Y. So the join X, and I need to get better at making an asterisk, but star Y. Is the union of all line segments joining points of X to points in Y. Another way to define this is the quotient space. Of X cross Y across the unit interval mod the relations are where R is X, Y1, 0, equivalent to X, Y2, 0, and I believe same thing, X1, Y, 0 is congruent to X2, Y, 0. Oh, nope, not 0, 1. So basically we're collapsing points to be at 0 and 1. So X cross Y cross 0 and X cross Y cross 1. And actually, I was slightly wrong. Basically, 0 collapses to X, and then 1 collapses to Y. And then a helpful picture here of like the join of, I guess, a cube. I'm like really trying to get better at art. Simply for the sake of doing better algebraic topology. If this is I, this is X, and this is Y, then the join X product Y, or no, the join X star Y goes to, I'm trying to draw this as accurately as I can. And the idea here does that. There you go, close enough. The idea here, collapsing things to like one corner where it's like just X at 0 on I, and then it's just Y at 0 on or at 1 on Y. So like basically this is still here, and then similarly Y has a copy there, and then everything in between is just I. So yep, a nice way to write points of the join of two spaces is with linear combinations. Nice way of writing points in X join Y is T1 X plus T2 Y with T1 plus T2 equal 1, and then 0 less than or equal to Ti less than or equal to 1. And then with, of course, 0x plus 1y is equal to y, and then 1x plus 0y is equal to x. And these are the corresponding like exact identifications in our like mod system. Yeah, so this makes it very easy to see. So you can do this with like n layers of this, right? You don't need to have just x and y. You can do this x1 through xn. And so basically this operation is associative and it works very nicely. The join of 2 points is a line segment. The join of 3 points is a triangle. The join of 4 points is a tetrahedron. The join of n points is a convex polyhedron of dimension n1 or n minus 1, and that is called a simplex. Similarly, the join of n standard basis vectors for an n-dimensional vector space is the unit ball, I think. Oh, no, it's just the unit simplex. Simplex. Basically for n points, n basis vectors are n, then the join of each vi basis vector I equals 1 to n is the set delta n minus 1, which is all of the points in Rn as a vector space. Such that the sum I equals 1 to n of ti is equal to 1 and ti is greater than or equal to 0. So I guess I was wrong. That is actually the positive region of Rn, the all positive region of Rn, and this is a simplex. Another interesting example is when xi is the zero sphere, which is, I guess, 2 points. If we take the 2 points of xi to be the 2 unit vectors along the ith coordinate axis in Rn, then the join is the union of 2 to the n copies of the delta n minus 1 simplex, and radial projection from the origin gives a homeomorphism between the n minus 1 sphere and then the simplex that we've constructed. And they keep changing the notation. That's a little annoying, but yeah. So now If X and Y are CW complexes, then there is a natural CW structure on X join Y, having the subspaces X and Y as subcomplexes, with the remaining cells being the product cells of X, product Y, product of the unit interval, excluding its endpoints. As usual with products, the CW topology on X join Y may be weaker than the quotient of the product topology on X product Y product I. So basically, yeah, mostly CW. So the next operation on spaces is called the wedge sum. And for Jorge and Zach specifically, I think this is something that we've talked about at the very end of our topology class. So given spaces X and Y with chosen points, so X naught in X, Y naught in Y, then the wedge sum X Vy is often what we'll call it, and I need to kind of make this a sharp V so it doesn't look like a union, because it isn't a union. Nope. Yeah, okay, that works. Is the quotient of the disjoint union obtained by identifying X naught and Y naught to a single point. So this is equal to X coproduct Y mod X naught similar to Y naught. And I'm pretty sure this is like gluing things together at a point. Yeah. This is just gluing things together at a point. This just glues things. So like the easiest example of a wedge sum is if you have two circles, yeah. And if we identify a point X naught and a point Y naught, then like we can glue them together like so. And this is the wedge sum X Vy. As a bigger example of this, for any cell complex X, for every cell complex X, the quotient x to the n mod x to the n minus 1 is a wedge sum of n spheres over alpha s alpha to the n, with one sphere for each n cell of X. With one sphere for each n cell. So our final operation on space is called the smash product. So, like suspension, this is another construction whose importance becomes evident only later. Inside of a product space, there are copies of X and Y, namely X product, a singleton set within Y naught, and then Y product, a singleton set of X. These two copies of X and Y intersect only at the point X naught and Y naught, and so their union can be identified with the wedge sum x vy. Their smash product, which is like that, is then defined to be the quotient x product y mod x vy. So it's x product y mod x vy is x smash y. That's like a really cool name. That's like kind of like it is a reduced version of the product obtained by collapsing away the parts that are not genuinely a product. The separate factors x and y. So then this is the product mod, the coproduct mod at a point. Product mod coproduct. Hold on. Smash product. Hmm. Um. So it collapses all of the trivial product parts to a point. Let me see if there's a picture on Wikipedia that's going to help. Yep, Wikipedia always has a picture. So we can, okay, here's a really good picture for it. So it collapses, okay, I'm going to draw the picture first, and then I'm going to do it. So given a torus, you know, on a torus, you have this outer ring, and then you have the inner line, which I'm not really drawing well, so I'm just not going to draw the inner line because it seems to be less important. But this is S1 prod S1. But then this gets smash producted by S1 smash S1, which is the product mod the V. And so what happens is we identify all of this as the X product Y naught, and then the X naught product Y. And identifying it that way lets us collapse it all down to a sphere. With like kind of a, if we were to put like lines on it, it would be like just tight. Like if you had stuff like going in there, it all like converges. I think my artistic ability is kind of holding us back here, but it's fine. And it all gets identified to this one point. Um, and then, okay, yeah, I guess as like an added note, x smash y is CW if x and y are CW and x naught and y naught are zero cells. Assuming that we have the cell complex topology on these things. And then as a remark, because this is not intuitively obvious to me, Sn smash Sm is equal to Sn plus m. In particular, when m and n are both 1, we see that collapsing longitude and meridian circles of a torus produces a two-sphere. And that is this example up here. And that's how we get this. Right, so this is S2. They don't put that in Wikipedia. Yeah. So this is where I would normally ask, like, if there are questions, if people need more examples. But I think we're chilling. Okay. So, this next section is called Two Criteria for Homotopy Equivalence. So two criteria for homotopy equivalence. So earlier in this chapter, the main tool we used for constructing homotopy equivalence was the fact that a mapping cylinder deformation retracts onto its target end. So by repeated application of this fact, one can often produce homotopy equivalences between rather different looking spaces. However, this process can be a bit cumbersome. In practice, it is useful to have other techniques available as well. We will describe two commonly used methods here. The first involves collapsing certain subspaces to points, and the second involves varying the way in which parts of a space are put together. So the operation of collapsing a subspace to a point usually has a drastic effect on the homotopy type, but one might hope that if the subspace being collapsed already has the homotopy type of a point, then collapsing it to a point might not change the homotopy type of the whole space. here is a positive result in this direction. So if x comma a is a CW pair with a contractible to a point, then x to x quotient a is a homotopy equivalence. A proof will be given later, like the very end of this. Yeah, like literally the very end of this. That's kind of crazy. But yeah, here we have some applications. So graphs can be homotopy equivalent. Like so. Since each is a deformation retractive a disk with two holes. But we can kind of deduce this from the collapsing criterion, that like we could like kind of cut this and then get this. And then we could like stretch this and get that. If the two endpoints of any edge in a graph with finitely many vertices and edges, if the two endpoints of an edge are distinct, we can collapse this edge to a point, producing a homotopy equivalent graph with one fewer edge. This simplification can be repeated until all edges of X are loops, and then each component of X is either an isolated vertex or a wedge sum of circles. And that makes a lot of sense. I don't think that's like a big... Yeah. So this raises the question of whether two such graphs having only one vertex in each component can be homotopy equivalent if they are not, in fact, just isomorphic graphs. Exercise 12 at the end of the chapter reduces the question to the case of connected graphs. And then the task is to prove that a wedge sum of one circles is not homotopy equivalent to the wedge sum of n circles if m is not equal to m. This sort of thing is hard to do directly. What one would like is some sort of algebraic object associated to spaces depending only on their homotopy type, and taking different values for the wedge sum of m and the wedge sum of n. In fact, the Euler characteristic does this, since the m wedge sum of S1 has Euler characteristic 1 minus m. But it is a rather non-trivial theorem that the Euler characteristic of a space depends only on its homotopy type. A different algebraic invariant that works equally well for graphs and whose rigorous development requires less effort than the Euler characteristic is the fundamental group of a space, which is the subject of chapter 1. Yeah, that's pretty interesting. That's like a neat little paragraph. As another example, we can consider, oh boy, this is a tough thing to draw, but I've got this. So this, I'm going to color two arcs. And this first arc we're going to call B, and this second arc we're going to call A. And let X be this whole space. And let this move off to the respective quotients X mod A and X mod B. Well, if we mod out, I'll start with B because that's kind of the easy thing. If we start out with B, then what we end up getting is we move the two endpoints. I'll just name them 1 and 2. That's not bright enough. What's yeah, that should work. Nope. 1, 2. Well, this contracts 1 to 2. And so that leaves us with a 2-sphere. I can do better than that. Leaves us with a 2-sphere that has the wedge sum at the identification 1, 2. Whereas if we collapse this thing down, what we end up getting is that there is this sort of hole in the sphere. I'm a little confused why. Hold on. So X can be given a CW complex structure with the two endpoints as 0 cells. Since A and B are contractible, the space X mod A is the quotient S squared mod the 0 sphere with 2 points. So I guess the idea is that all of the space, all of the space in here, there we go. That's the piece that goes missing. Like A gets joined in from being like a 1 cell. Right? Hold on. See, this is why I like algebraic geometries because I don't have to visualize as many things. I've always been bad at visualizing things. You can ask my high school geometry teacher, Mrs. Sturdy, and she would probably say that I've never been that great at visual geometry. um, Basically, it's gonna look like this. And hopefully it's clear that there is a big hole here. And so yeah. And this is X mod A. Let's see. So the 9th example, which is this 3rd example, is if we let X be the union of a torus with n meridional disks. That's a new word. Meridional. Who's ever heard of that? That's like okay. It looks like wait, what? Hold on. I'm confused. Meridional. Hold on. I can't tell from the picture what meridional means. Meridional. Relating to a meridian. Oh, all right. I get it now. Okay. So consider X to be the space that is a torus like so with meridional disks, and now it will be clear. Like that. And then collapsing each of these to a point takes each of like these middle sections. I guess let me do these in different colors. It takes each of these middle sections of the torus and turns it into a space Y, which is 4 one-spheres, which each touch at a point. And I'm realizing that there is a really weird perspective thing going on here. So if you start with the bottom sphere, and you make it clear that these two spheres touch. Maybe I ought to just copy. There we go. Like if we identify these by 1, 2, 3, and 4, and like maybe this is 1, and then these are also spheres, and then the back. This is where I have to not screw up. And so like looks like this. And so 1 and like 2 would be back there. 3. Actually, I guess that would be 4. And 3 would be right there. Then it like collapses into Y. And then the third space is like you can like turn these into beads on an arc. And it goes on, like you can do more with this. But I'll just stop here because that's a lot of drawing. As a, I believe, fourth and final example of all of this, there is reduced suspension. So if X is a CW complex and X naught is a zero cell, then inside of the suspension we have a line segment defined at X naught that we can collapse to a point. So let X be CW, X naught in X, be a zero cell. Then in the suspension of X, there exists the line segment X naught cross I, and collapsing this to a point, yields sigma x, which is the reduced suspension. So again, just to recall what a suspension is, it is basically the collapsing of x cross I to 0 and 1 respectively. So it's like closely related, but it to the first thing that we defined today, the I believe the wedge sum. Yeah, no, just to the join. It's related to the join, but it preserves the entire unit interval. Um, and so basically because it preserves the unit interval, we have this line segment. Collapsing the line segment to a point is the reduced suspension. And I guess that's just one way of thinking about. I don't know what like the import. Like I can see that it must be important. Kind of missing the point though. Um. Okay, he gives an example. Maybe that's going to be more helpful. So consider the one sphere wedged the one sphere at a point x naught. Then as the suspension is just two circles joined at a point. Or rather, sorry, not circles. I should know this at this point. It's two spheres joined at a point x naught, and so then the line segment is the union of two spheres intersecting along the arc. Oh, it's not. This is the reduced suspension that I just drew. But maybe this is like x naught cross 0. This is x naught cross 1. And then the reduced suspension, sigma x is just at x naught. And then just as a fact, the reduced suspension of xvy is equal to the reduced suspension v the reduced suspension. For arbitrary CW complexes. The CW structure of reduced suspension is easier to kind of understand than the general suspension. In the general suspension, there are two zero cells, the two suspension points, and an n+1 cell for each n cell e to the n of x. Whereas in the reduced suspension, there is a single zero cell and just one n+1 cell for each n cell of x other than the zero cell, x naught. The reduced suspension is actually the same as the smash product, x smash the one sphere. Since both spaces are the quotient x cross the unit interval mod x cross the boundary of the interval union, or is that cup? I don't know. X naught cross the unit interval collapse to a point. And I don't know if this is union or the cup product. Who knows? Probably, hopefully me in like 2 weeks. So this has all kind of been an example of the first way to contract spaces for homotopy equivalence. So the second way to contract spaces is attaching spaces. And so this involves the idea of continuously varying how its parts are attached together. So a general definition of attaching one space to another that includes the case of attaching cells is the following. We start with a space X, so start with a space X naught and X1 that we want to attach to each other by identifying points in a subspace. So identify points in with X naught. The data needed to do this is a map from A into X naught. So need F from A into X naught, because then we can form a quotient space of X naught coproduct X1 mod A similar to F of A for every A and A. And we're going to denote this X naught. I don't know what to call that. Basically, it just identifies points with their image. So let me, I guess, formalize A and A, which is a subspace of X1. This is the space X naught with X1 attached along A via F. And then as a remark, when X1 comma A is a CW pair that is the N disk paired with the N-1 sphere, this is attaching an N cell to X naught via F Sn-1 to X naught. So an example of this construction is a mapping cylinder. And actually that's a pretty obvious one. That's like a good way of doing that. Closely related to the mapping cylinder is the mapping cone, where you're attaching like a point to a space. Or rather an N-1 cell to a space. Like in 2 dimensions, it's in a 0 cell. If one varies an attaching map by a homotopy, so I guess this is a remark. If we vary the attaching map F by a homotopy FT, we get a family of spaces whose shape is undergoing a continuous change, it would seem. And one might expect these spaces to all have the same homotopy type. If we have a CW pair, X1 and A, and two attaching maps which are homotopic from A to X naught with F homotopic to G, then the attaching map, that's what we'll call it, the attaching map F, is homotopic to the attaching map of G. So we're going to defer the proof one more time until we have this thing, I think, called the homotopy extension property. Dude, I'm going to be so happy when we get into commutative diagrams because I cannot visualize this. Like, diagram chasing is a pain, but I am not good enough at visualizing things for this. So yeah. Okay. We can read what's example point 8. So this example up here, the orange and blue with X mod A, X mod B. A sphere with 2 points identified as homotopy equivalent to S1V S2, where S1 is a circle, S2 is a sphere. We attach along the curve B. Which okay, I'm not sure I'm gonna be able to explain that spatially. I don't know. I wish I could draw this stuff better. Okay, here is a less pictorial view. So let's do that example. So here's an application of the earlier fact that collapse into contractible subcomplex is a homotopy equivalence. If XA is a CW pair, then X mod A is homotopic to X union, I'm assuming this is a union, the mapping cone of A by the inclusion of A into X. And so basically, like, X mod A is equal to X union CA mod CA, which is homotopic to X union CA. Because basically the mapping cone is like the most obvious contractible subcomplex of X union CA. Yeah. So now we have 4 pages left in this chapter, which I feel like is pretty good. The other thing I want to do today is I want to just scan through some of the exercises, um, and see if there's any like really important ones that we should do on the video or that I should just email out to our little email chain. Um, yeah. So this next subsection is called the homotopy extension property, and that's getting abbreviated. Extension property. And if I had to guess, this is basically just gonna say that if if one map is homotopic, like transitivity. Um, but I don't know. So consider the following problem. Suppose one is given a map f naught from x to y, and on a subspace of x, one is also given a homotopy from a to y of the restriction map on A that one would like to extend to a homotopy of the given f naught. That needs to get written down. So consider f naught from x to y, and on A subspace x, we're given a homotopy ft from A to y of f naught restricted to A, that we want to extend to ft from x to y, for f naught. So we want to extend this partial homotopy to be a full homotopy. If the CW pair is such that the extension problem can always be solved, can always find such an extension, then XA has the homotopy extension property. That's a weird way to put it. I.e., for every map f from x cross 0 union a cross I to y has an extension ft to x cross I to y. And so then, like, this is a retract of this within X. The converse is also true. If there is a retraction going backwards, then by composing with the retraction, we can extend every map with the homotopy extension property. This implies, for example, that if a CW pair has the homotopy extension property, then so does its product space. And this is just, I guess, a lemma. if XA has homotopy extension property, then so does X cross Z and A cross Z for every space Z. Wow, there's just so much in this text. If XA has homotopy extension property, A must be a closed subspace of X. I'll clarify that. Closed subspace of X. If X is Hausdorff. Basically, if we're given a retraction onto this space here, then the image of the retraction is the set of points in X cross I, such that it's a fixed point. So the image is a set of fixed points. And then a closed set, so the image of the retraction is a set of fixed points, and then the retraction is closed in that because of something to do with Hausdorffness, but I imagine that that would be a longer proof. A simple example of a pair with A closed for which the homotopy extension property fails is the pair of the unit interval and A, where A is all of the rational numbers 1 over an integer. It is not hard to break down that there is no continuous retraction of I cross I into I cross 0 union A cross I. The breakdown of homotopy extension here can be attributed to the bad structure of A near 0. With nicer local structure, the homotopy extension property does hold, as the next example shows. So, I don't know. This is interesting. I'm trying to think through, from like an analysis context, this business of, so like, hold on, how, wow. So if A is the set 0, 1, 1 half, like 1/3, I guess I should clarify. 1. There is no continuous retraction. Yeah. So the next example says, okay, a homotopy extension property does hold. Let's show it. So a pair X and A has the homotopy extension property if A has a mapping cylinder neighborhood, or rather there's a homeomorphism from the mapping cylinder onto a closed neighborhood of the subspace A, where the restriction map of the homeomorphism is the identity. and the homeomorphism of the mapping cylinder minus the original space is an open neighborhood of the subspace? That doesn't make sense. Hmm. I'll be honest, the words are starting to swim on the page. I'm gonna take a 5 minute break because we're kind of going ahead of schedule. I'm gonna come back and I think we will be able to tackle this example. Okay, so settling back in, let's go ahead and take a look at this example. So XA has homotopy extension property if A has a map F from Z to A and a homeomorphism H from the mapping cylinder onto a closed neighborhood N A in X with H restriction to this is the identity on A and with H of the mapping cylinder minus Z is an open neighborhood of A. Mapping cylinder neighborhoods like this occur more frequently than one might think. For example, the thick letters discussed at the very beginning of the chapter provide such neighborhoods of the thin letters regarded as subspaces of the plane. Interesting. Yeah. So proposition, if X and A is a CW pair, then X 0 union A cross I is a deformation retract of X cross I. Hence, X comma A has the homotopy extension property. So I think that he provides proofs starting here, because there's like four main proofs of a few propositions up here. And these are kind of maybe boilerplates for the other things. So let's go ahead and go through the proofs. So there exists a retraction from the end disk cross I to the end disk cross 0, union the boundary of the end disk cross I. For example, radial projection from point 0, 2 in the disk cross R. What? Oh, I see. Okay, then RT is equal to TR plus 1 minus T ID on DN. Gives a deformation retraction of, yeah, this is the deformation retraction. And then this gives rise to a deformation retraction of X to the N cross I onto X to the N cross 0 union X to the N minus 1 union AN cross I. since x to the n cross I is obtained from x to the n cross 0 union x to the n minus 1 union an minus 1, no, an cross I by attaching copies of the n disk cross I along dn cross 0 union the boundary of dn cross I I guess that should be a comma. So basically, like, the whole plot here is that we're attaching things to spaces. If we perform the deformation retraction during the time interval, wait, what? Hold on. So performing the deformation retraction RT on T in 1/2 to the n plus 1, 1/2 to the n. This infinite concatenation of homotopies is a deformation retraction of xi onto the terrible thing. Gives deformation retraction onto okay, so how the hell did they come up with that interval? So if we were given this original retraction, like all of this stuff, then we're doing basically a linear homotopy from the retraction to the identity map. And this looks like just doing this over every single disk, over every n disk. And so from a cell structure, from a cell complex structure, I think that we're basically just retracting every single boundary of each n disk up to the n minus 1th disk. At which point we attach the rest of it. That's like horrible notation though. Like, I don't know if I would ever have come up with that. There's no problem with continuity of this deformation retraction since it's continuous on x to the n cross I. Yeah, okay. Interesting. That's going to take some adjusting too. Yeah, so now we can prove an earlier assertion that collapsing a contractible subcomplex is a homotopy equivalence. I think we started with this. If XA satisfies the homotopy extension property and A is contractible, then the quotient map Q from X to X mod A is a homotopy equivalence. Yeah, so this was the one way up here. I swear we did this today. can do this today. Who knows? So let's prove it. Let ft from x to x be a homotopy extending a contraction of A. Extending a contraction of A with f naught is equal to the identity on x. Then, since ft of A is contained within A for all t, the composition qft from x to x mod A sends A to a point. And hence factors as a composition x by q to x mod A to by ft bar to x mod A. What? Where ft bar is I guess gives that the inverse composition q ft is equal to ft bar q. Not sure where that plays into this. So here they have some diagrams, and this is where it's hopefully gonna make it so that I can explain this well. So ft goes from x to x, q goes to x mod A, q goes to x mod A, ft bar goes from x mod A to x mod A. When t equals 1, then f1 of A is a point. The point to which A contracts. So f1 induces a map g from x mod A to x with gq equal to f1. And this is in another diagram. X by f1 to x goes to q, or goes by q to x mod A. And then x mod A goes down by q, goes up by g to x, and then this is f1 bar. It follows that q composed with g is equal to f1. And so then G and Q are inverse homotopy equivalences. Since GQ is equal to F1, which is homotopic to F naught, which is equal to the identity on X via FT. And then Q composed with G is equal to F1 bar, which is homotopic to F naught bar, which is equal to the identity on X mod A via F of T bar. Okay. I don't think I understand this proof. So we're trying to show that if a pair satisfies a homotopy extension property, and we have a contractible subspace, then the map into its quotient space is homotopy equivalent. And so what this means is that like all of the deformations lie within A. There are no deformations outside of A. And so we're saying if we let the F naught map be the identity that's given by the homotopy extension property, then we can fix Q to go to a point within its mod. What? X goes to X mod A by Q, which has FT bar and what we're trying to do is we're trying to show that since F1 of A is a point, we get G at 1. It goes back to X that looks like F1. Yeah, because it's modded out by a point. And so we're like identifying that with A. And then G and Q, F1 is homotopic to F naught, which is the identity map. Yeah. In the mod, it's homotopic to the identity map. And then its inverse is homotopic in X. And since the composition of those two things are homotopic, the composition of homotopic equivalences are homotopic equivalences. Okay, I'm still not entirely sure I get it. I'm gonna think about this more tonight. My brain is kind of starting to taper off. What I want to do is I want to state the last 4 propositions and maybe get through one more proof. And then I can always just pick this up tomorrow and kind of comment on the proofs and like walk through them. So, yeah. Proposition. If x1, comma A is a CW pair, and we have attaching maps F and G from A to X naught, um, with F homotopic to G. Then X naught attached by F to X1 is homotopic to X naught attached by G of X1 relative to X naught. And the definition of W homotopic to Z well to 0y. W homotopic to Z rel y for pairs WY and ZY is such that there exist maps phi from W to Z and psi from W to Z, or psi from Z to W. Restricting to the identity on Y. Such that phi or psi composed with phi is homotopic to the identity on W, and then psi phi is homotopic to the identity on Z. And then, yeah, the next proposition is let's have pairs with the homotopy extension property such that F from X to Y is a homotopy equivalence with F restricted to A equal to the identity on A. Then F is a homotopy equivalence relative to A. And then as a corollary, if the pair X and A has a homotopy extension property and the inclusion A into X is a homotopy equivalence, then A, say deformation retract of X. Yeah. I think that makes sense. My silence is just kind of trying to think through it. Yeah, this is probably where I'll start tomorrow. As a final corollary, a map f from x to y is a homotopy equivalence if and only if x is a deformation retraction of the mapping cylinder MF. Hence, x and y are homotopy equivalent if and only if there exists a third space Z containing x and y as deformation retracts. And I think I'll start tomorrow by proving these. So thank you so much for watching, and I will go through the problems and attach them, I guess, probably to the description of this video. And yeah, cool. Thank you.